I guess, look, in terms of facades and fire safety engineering, we really have to look at how it has changed over time. In fact, even how we've been involved in doing any fire engineering with facades. The best way to look at this is look through a timeline. Look at the events that have really shaped changes in response to fire engineering, building surveying or certifiers responses, and seeing how basically, like most building regulations, when there is a crisis or there is a disaster, people respond and attitudes and processes change. Now, I started doing fire safety engineering in 1997, and basically, if we go along a timeline here, I'll just see our, oops, sorry. So make sure my circle, okay. So if we go from 2000 to 2014, the lacrosse fire. Through that time, there was one single fire engineering report where we actually looked at fire spread via a facade. After that, obviously with lacrosse, suddenly we're thinking about combustibility. Grenfell disaster introduced other considerations, including combustibility. And now, suddenly we've got a new NCC which starts to consider combustibility, facade tests and the like. So everything, unfortunately, with regulations and compliance approval, and ultimately our involvement in that process as fire safety engineers, has come as a consequence of basically disasters. Now, the compliance requirements for facades, and certainly for fire safety, are basically controlled by the building code. Now, basically the BCA 90 was introduced to get a uniform building code across all states in Australia, and then it's evolved through time to our now NCC 2022. Each of these have slowly changed the requirements for combustibility, for requirements to test facades for combustibility, and the processes you follow to approve them. Now, the key fire issues with regards to facades from a fire viewpoint are really two important points. The first is the combustibility of facades. That comes from the lacrosse fire. We've had other fires in Melbourne, in the Neo 200 fire, and obviously you had the Grenfell, and there's been numerous fires overseas with high-rise buildings and facades. And the prime use of that was the ACP, aluminium composite panels. The ACPs were largely polyethylene core, would burn very well when exposed to large flaming fires. Other issues with combustibility of facades, which are a little bit more hidden, is actually how you build the wall. There are practical requirements when you build a facade. You're going to have sealant, you're going to have insulation, you might have packers and shims and all sorts of bits and pieces that actually make the facade so you can build it. A lot of that's ignored in the BCA, it always has been, because they're very minor issues. The second important thing when you build a facade is essentially the continuity of the fire separations to the outside of the building. The building code assumes that when you have a concrete slab separating two levels, that concrete slab goes right to the outside of the building. Therefore, if there's a fire in that lower level, it's got to go out of the building and then break back in. And what happens when you have a curtain wall system, the fire can break. It doesn't necessarily break out, it will enter the facade, and the facade becomes like a little chimney, and it can spread through with actually going outside the building. And so these are the two key fire issues, and the events at Lacrosse and also the Grenfell fire brought both of those things into sharp focus for people. Now, these are some of the buildings that I worked on where we had absolutely no fire engineering involvement. They're large buildings. That one I think is about 68 stories. Large, I think I worked on about 3 of these. Absolutely no involvement of the fire engineer. Curtain wall systems, they've got cavities, and the building surveyors, certifiers approved it. The other different process we had with a number of these buildings is the facade engineering was completely separated from almost the rest of the design team. You'd have your primary architects, they may set a specification for a facade, then a completely independent practice would come in, design a facade and almost bolt it on. It was very disconnected with the whole approval process of the building. So they sort of slip through the cracks, a lot of facade designs, in terms of regulatory compliance and looking at the issues of the fire spread. And the other processes in not having fire engineers were certifiers and building surveyors were accepting having your ACP's combustible cladding. There were provisions in the BCA that they were using, which probably weren't the right processes for approving it, but that were the tools they were given under the BCA. And these are some of the reasons of why they approved it. There was a concession for attachments that are combustible in the BCA. There was a concession for composite laminates, which people said that ACPs could fall under this one. And as I said before, when I'm talking about all these little minor elements of the facade, the little bits and pieces, there was a section in the building code that basically said you didn't need to look at them under a specification, but this actually wasn't related to combustibility. This was related to linings and performance of internal linings of materials, but that's how they were used. And the second thing with the continuity, the second primary issue and spread between the cavities, is the building surveyors would approve a facade system, a curtain wall system. All they wanted to do was have a smoke separation between the edge of the slab, like it might just be some fire mastic, that would go to the back pan of a facade system, and they considered that acceptable for a sprinklered building. The only mention of curtain walls under the BCA, or National Construction Code as it's called now, was with a building that wasn't sprinkled. These are low-rise buildings, and this was a spandrel protection. There was absolutely no guidance for a sprinkler-protected building or mention of how you treat a curtain wall. And this sort of gives you an idea. This is the only part of it with the spandrel. So this is a fire-rated element. You need a 900mm high spandrel to separate the level, to stop the fire breaking out of here and coming up the top. And it's just saying non-combustible material. Somehow this is packed inside your curtain wall. So there's no real detail. But that was all that was mentioned in the building code about how you deal with curtain walls. Didn't do much for, a 50-storey building, because it just isn't even called up under the NCC. So when did the combustibility of facades really come out? Well, this was in 2014. This was the La Crosse fire. Before that, nobody really turned their mind to it. The proprietors of the aluminium composite panels had been, I guess, looking at this as being maybe an issue, because code marks were issued in 2013 for ACP panels that were largely fire retardant. But the regulations in Australia at the time didn't really push it. So people would tend to use the more combustible panels. So once you had La Crosse, then we had the regulators, VBA, Australian Building Codes Board, CSIRO, introduced industry alerts, drawing to attention. These materials are highly combustible. You shouldn't be using them on facades. The way the building code was being used as a combustible attachment, using a small-scale test like AS 1530 Part 3, which would not tell you how a large fire would actually affect an ACP. They called that into question. You couldn't use it. There are also issues about what's a wall, what's an attachment to a wall. And certifiers and building surveyors would all argue about where does the wall stop, when does the facade start. And as I said before, the test they used, because the small-scale test that was referenced in the building code, it wasn't intense enough to melt through an aluminium panel to get into the combustible core. So you couldn't actually differentiate between that one that didn't burn well and one that burnt very well in a real fire, because you couldn't get through the aluminium. It just reflected the heat back, wasn't big enough. And basically that meant, well, there was no appropriate facade test standard in the NCC, in the building code. And the second big issue, when did that come to the fore? Well, that came to the fore, as I said before, in the Grenfell fire. So, Grenfell was an absolute disaster. This had a multiple of issues that caused this to occur. It had no sprinklers. You can see the height of the building. You can see the little fire hoses there. Firefighters can't manage a building which is this tall. No sprinklers. You won't find many buildings in Australia of this height without sprinklers. They'd probably count them on one hand. They'd be very old high-rise buildings. Combustible materials on the facade and combustible insulation. And the third issue was they bolted the facade on and had a cavity between the old facade where they put insulation, and then they had their combustible aluminium composite panel with a 50mm gap. That made a chimney that ran right up the front in the face of the building. And an important point when we look at this, and I'm going to, we'll just have a look. So this is what happened with the Lacrosse building, the Grenfell building. As you can see, fire comes up. Now what happens, makes it even worse, is when you've got an ACP, which is highly combustible, and you've got an insulation foam on this face, the radiant heat feeds back on itself. So it actually makes the fire even more intense as it goes vertically. And obviously, when you're going up in this chimney, it allows the fire to enter the building. The heat's not going out and looping around. It's going very close to the facade, which means it very rapidly can enter the windows and spread fire through each level of the building. An important point to stop that is that you have to put a cavity barrier in there. So you have to block the chimney. So it can't continue to just go up through that gap in a curtain wall system. And all the tests that were done to approve our ACPs, the ones that actually don't burn very well, they all actually had cavity barriers in their tests. Unfortunately, the code marks that we got and the systems that were documented in those code marks didn't have cavity barriers put in them. So what happened as a consequence of all these events? With the certifier and building surveyors, they had to tighten up the processes they used to approve buildings. As I said before, there were industry alerts that were issued by the ABCB, Victorian Building Authority, and various other state legislative bodies that control building regulation. And the second thing that started to present itself was now the certifiers were asking fire engineers to consider the fact that the fire ratings did not go to the outside of the building. How was fire going to be stopped going up through the facade? Something that hadn't been asked for certainly the first 15 years of my career. And the other response was, there was a knee-jerk response when they brought out the NCC or BCA 2016 Amendment 1. They were very strict on what you could do for a combustible or non-combustibility for a wall. And this included impacts on things like sarking. We suddenly had to have sarking that had non-combustible, completely non-combustible sarking, which had certain impacts in terms of environmental issues in the wall cavities. And there are also all these minor construction issues, elements I talked about before, in terms of the things you use to build a wall. When the BCA or NCC 2016 Amendment 1 came out, it almost became impossible to build a wall system practically. And so by the time the NCC 22 came out, a whole lot of new things were introduced, and there's a whole lot of things I've listed here, you can see here, that's straight out of the NCC 2022 that basically allowed you to put the sealants in, gaskets, caulking, and it just meant that it was more practical. But it does take time. Regulations in Australia, unfortunately, are a response to a crisis. So now for current buildings, if we're using a current National Construction Code, the NCC has addressed in clause C2D10, it's allowing minor elements for practicality to be combustible. And the other element is that in general we don't use combustible elements on the outside of buildings for our cladding. So combustibility in a lot of ways I think has largely been addressed because it's being looked at very closely. There's a lot of scrutiny. If somebody wants to put some sort of combustible material, it's looked at with a lot of scrutiny by fire engineers, by certifiers, and also the fire brigades as part of the approval process. So a lot of those issues have been addressed, I think. And if they're not, they are looked at specifically. So things don't slip through as easily as they used to. And the other key issue is the continuity of the fire barriers. Now, continuity of fire barriers, well, I'm talking about slab edges, but if you do hospitals or apartments, you've got a fire-rated wall between each apartment. And again, that's got the same problem about not extending to the outside of the building. You're always going to have probably some sort of a curtain wall structure in front of it. So again, that's that lack of continuity. The way we have to look at that, there is really no deemed to comply solution. It has to be looked at through a performance solution with a fire engineer and a certifier, and then the fire brigade will get involved in the process in that approval. There is one alternative way you can satisfy the performance requirement for fire spread, and this is a verification method. This is one way you can do it, and this is where you can actually do a full-scale test of your facade. And if you satisfy the rating, the facade performs and doesn't spread temperature up it and measured in this test, you can satisfy the verification method, C1V3. Of course, this is not practical for most buildings because each facade element will be unique. You can't go and spend $50,000 and do a facade test for facades that are generally bespoke on buildings. However, some people have a standard system, a standard facade system, and in that instance, it may be appropriate that you can do a facade test and demonstrate that it complies with C1V3, and that's just basically would be approved almost straight away. So ultimately, each building ends up with a bespoke solution to address fire spread, because each facade system we see is unique, and we have to look at the way we deal with that issue of fire spread via the cavity spaces. You have metal flashings to restrict fire spread. A lot of the time there'll be a rock wall system incorporated into the facade element to restrict spread through the cavity. But of course, a lot of these cavities, they've got issues. You don't want to retain water, you want them and you want them ventilated. Once you start doing that, you're looking at things that need to swell up and seal up fire spread through that cavity. That's where you end up with things like intumescent strips and sealants. So when fire hits those, they swell up dramatically and they'll seal up a gap. You've obviously got to make sure that they're with the suppliers of those systems, that they meet the weatherproofing requirements. You don't want them to go off or deteriorate or not be able to stay in place for moisture and hot weather. There are a number of systems that have been developed by building suppliers. Bradford have a fire seal, Trafalgar have got their side rise product, and Trafalgar have got a number of different solutions. I think they came to our office yesterday and showed us some of their solutions for some of the ventilated facades where they've got the rock wool and an intumescent. But the space has now got products to deal with these issues of fire spread that maybe 10 years ago they didn't exist or nobody cared about them. I mean, these are some of the examples. This is the example of a party wall between two apartments. This solution, they stacked it full of plasterboard. And I've put some intumescent sealant in there between the glass. I haven't seen anybody pack a gap like that full of plaster ever. I don't know how that goes after a few years in the weather. The same building, they went for a more conventional approach where they've got flashing, they've got rock wool to restrict spread. This is horizontally through that side of the apartment, going through the cavity and then coming out the other side. So, as I say, everything's fairly bespoke. A lot of the work is the facade engineer needs the facade to work properly, and then we've got to look at how we deal with the fire spread issue. It's almost secondary. And there's a typical one for a slab edge type facade protection, same sort of issue. There's your slab edge here, and the fire, you've got to really block it from coming around and leaping through the inside of the facade. So this will have metal flashing. It'll have rock wool cavity barriers to deal with that spread. So ultimately, with fire safety engineering, we're now getting involved on almost all projects. This is always an issue we have to look at. Generally there is no deemed to satisfy solution. So when you're designing facades, this issue will have to be looked at, and it's probably, there needs to be consideration of the practicality of the method of dealing with the fire separation, but obviously you need your facade to work properly as a facade for your intention. And that concludes my talk. Thanks for that.